We started the Colloquium, and our speaker is David Wolpert of the Santa Fe Institute, and he's going to be talking about the stochastic thermodynamics of distributed systems. So David, you can grab the screen.
Let's see. Okay, so starting it all over again. First, we have the movie of me and my dog, the best dog on the planet, where I am feeding my dog. So I'm just sitting there, my dog's eating. So my dog is an evolving subsystem, and I am a fixed subsystem, B. And during the process, I don't change, only my dog changes. It's called a solitary process if in addition, the entropy flow at a trajectory level is given by just the entropy flow of each subsystem separately. There's no interaction between me and my dog, no interaction Hamiltonian. So the total entropy flow is that due to me plus that due to my dog. In any solitary process, the entropy production at the trajectory level is the
David,
never mind the silliness about the dog. I wonder what caused pause share. Anyway, okay. Two systems evolving. It's called a solitary process. That means that one system is fixed in its state and the other subsystem is the only one that's evolving. The other part of the definition is that the entropy flow can be written as just the entropy flow of the two subsystems separately. In any solitary process, the total entropy production in the conventionally defined sense is the sum of the entropy productions of each subsystem considered by itself minus the drop of mutual information between the two subsystems during the process. And down below, to avoid all messy equations, I'm just going to assume for simplicity that the entropy production of subsystem B, the one that's fixed, is equal to 0. Okay, so the slides are changed. I hope, okay, I'll take silence as assent. It can be shown that with this formula, that the entropy production of subsystem A, that means this term here, its ensemble average is greater than or equal to 0. That means that in general, the entropy production of the entire system is lower bounded by the drop in mutual information, and by the data processing inequality, one can show that that's positive. Crucially, all the fluctuation theorems and uncertainty relations apply to just the subsystem A, for example, in the solitary process, if we take the entropy production to be just its entropy production by itself. That should be contrasted with some earlier work that was done by Tsusuke and Takahiro, where they looked at a similar process, but they had a slightly different definition of entropy production, where the entropy flow associated with the subsystem I was the entropy flow of the entire system, rather than just doing everything restricted to looking at only the subsystem I by itself. In particular, the second law for this definition of entropy production doesn't hold. This thing can be negative. And in fact, there's a lot of ways that this is related to things like transfer entropy that was investigated in that paper. Because of this, the fluctuation theorems and the thermodynamic uncertainty relations, the speed limit theorems, and so on and so forth, if we use this definition of entropy production, none of those actually need hold, whereas they always hold with this definition of entropy production. Okay, so that's a little bit of a background. What are the implications of this little two subsystem scenario? Well, as we evolve a system through time, we can actually change, we can at any moment, if only one set of variables is allowed to change, we can say that that is the evolving subsystem and everybody else is the fixed subsystem. Then as we change who it is that is the evolving variables, we can simply flip that definition, and all of those previous results concerning solitary processes would go forward. And this is a way to actually analyze the thermodynamics and fluctuation theorems and uncertainty relations and all the rest of it for multi-system Bayes nets. What I mean by a multi-system Bayes net, if anybody knows that from what a Bayes net is from machine learning, it's a way of being a little bit more precise about what the variables in the Bayes net mean in a physical real world. So for example, here I've just used colors to indicate different physical systems. So light blue is one physical system, tan yellow is another, here's tan green, and here is a update. It's a fixed sequence. And what these arrows are all indicating is that, for example, right here, at this instant, the blue system updates its state according to a conditional distribution that depends on the existing state of green and blue, but is conditionally independent of the state of tan. Over here, tan, once this has completed, it's not allowed to happen before, the tan subsystem is up. What this graph illustrates is that after that, the tan subsystem updates its state based upon the fixed state of blue and tan's own previous state, and also the earlier state of blue. So both states of blue can, both the earlier and the current state of blue can affect the current state of tan. The crucial thing is that at any particular one of these nodes, we can say that that node is the evolving part of a solitary process, and everybody else is fixed. So they are the fixed part of the solitary process. That allows us to do the thermodynamics within each node separately, and by just summing up all the associated values of entropy production, we can actually get the entropy production for the overall system. So a little bit more specifically, let's consider this part right here. This means that this is an illustration where the green node at the end, its final state is determined by its earlier state and also the earlier state of tan. The implicit assumption in this earlier work, a very good paper by Takahiro, by Suzuki and Takahiro, is that the entropy flow generated by running this node only depends upon the states of its parents. It's independent of all the other ones, as I earlier said. So we have a solitary process when that node runs, where V and the parents of V are the evolving part. And that's the assumption that I'm making here. Here's another illustration. When that node updates, this right here is the evolving part of the solitary process, and all of that is the fixed part of the solitary process. So given all that, what we get, it's not too hard to show, is that the entropy production at the trajectory level for running the entire system is the sum of the entropy productions of every one of the solitary processes when it runs. So for example, right here, this is the solitary process where yellow is updating its state while these three are fixed, minus the change in the mutual information between that system and the rest of the overall Bayes net when that system changes. So this sum right here, V is running over all the nodes in this Bayes net, and this right here, these are the drops in the mutual information between the associated evolving subsystem and everybody else when that particular node V updates itself. Okay, I have no idea what's going on with time given those technical problems in the beginning, but I'll just plow on through and see where we go. As I was mentioning, because of this careful definition of entropy production, which differs from what was done before, all the normal fluctuation theorems and uncertainty relations and speed limit theorems and stopping time theorems, all of that applies at the level of the overall system. So for example, we have an IFT, an integral fluctuation theorem, saying that the sum over all nodes in the Bayes net of the entropy production generated by running just that node by itself, minus the drop of the mutual information when that node runs, summing that over all nodes, that equals 1. So if we do that, for example, in this particular in the sum here, this would be one node. We're summing over the entropy production there and the drop in mutual information between these three and those five. We're summing that with the entropy production generated within the pink circle here, and the drop in mutual information between these four and those four. We sum it all up, and that's what's going on in the exponent there, and we get a normal fluctuation theorem. These fluctuation theorems, this is at the level of the trajectory of the entire multi-system Bayes net, the fluctuation theorems, as I mentioned, they also hold just when each individual node by itself runs. So notice that this right here is only for one specific one of the nodes in that Bayes net. Okay. And I guess I should have prefaced that Bayes nets, they actually exist before it was really called machine learning even. They're rather old, what's called a graphical model in statistics. They are a way of modeling a vast number of systems in the real world. And all of these equations, these are exact equalities, they hold up in the real world. They hold, for example, when I was having that interaction earlier with my dog, that particular Bayes net, these fluctuation theorems apply to that and to many, many other scenarios. They are one of the most common tools in what is these days sometimes called artificial intelligence, because they model just about everything you encounter in your day-to-day life. In addition to the fluctuation theorems, because of this careful way of defining the entropy production in a solitary process within the Bayes net, that means that, as I was mentioning, thermodynamic uncertainty relations also apply to multi-system Bayes nets. So to give a simple example, we can suppose that the Hamiltonians and rate matrices, the sequence of them, cause the overall system, the overall multi-system Bayes net, to be in a non-equilibrium steady state. It's not hard to do that, actually. We can then choose JV in the normal way to be any current concerning only the subsystem V. And we have a thermodynamic uncertainty relation for just that subsystem V, for just that nodes in the Bayes net. So this would be, for example, remember, this is subsystem V. And so that would be a current concerning these four nodes, not concerning any of those. It's just a current when these four nodes update. That's what this JV would be. It is greater than or equal. So the entropy production when V runs is greater than or equal in the normal way to twice the precision of that particular current. And we can therefore use this to say that the entropy production of the overall multi-system Bayes net is lower bounded by the sum over all the subsystems, not just of the statistical precision of the current when that subsystem runs, but we subtract off that term, the mutual information when subsystem runs, the change in the mutual information between that subsystem V and all the other subsystems in the multi-system Bayes net. So I think I probably don't have enough time given those technical problems at the beginning.
You have actually, I'm accounting for them. So you have 17 more minutes for your talk and then 15 more for the questions.
Okay.
We started at like 7 or 8 past 3. There was a huge thing. So yeah.
Okay, let me see if I can maybe try to do this. I'll be conservative. I'll skip past this example. This is an example working through it, where this is a very, very simple multi-system Bayes net. The idea is, that first this system updates right here. This one updates based upon those two. And then after that, this system updates based upon those two. So we don't have, you're not allowed to in a Bayes net have them update simultaneously. In this very, very simple example that I work through here, we're assuming that the state of B does not change throughout the entire process. And we're setting up the conditional distributions of how A updates and how C updates. For simplicity, we're assuming that they're actually identical, that A and C live in the same size space, and both of them update these conditional distributions at this node and the conditional distribution at that node. They're identical, except they just concern, in this case, updating the state of subsystem A, and here you're updating the state of subsystem C. So they just evolve in the same way to make things be very simple. And then if we just use time homogeneous rate matrices and so on and so forth, then what we end up, what's actually going to be happening is at the end of the day, if we start with subsystem A and subsystem C in the identical state, let's just say that that happened. After this process, they would end up in general in being in different states. The coupling that they had, statistical coupling in the beginning, is lost by the end. That means that there's going to be non-zero drop in mutual information in general in this particular process. If we also are at a non-equilibrium steady state, that means that for any current functions we choose, a current function concerning just subsystem A and a current function concerning just subsystem C, the overall entropy production of the entire basenet is lower bounded by the sum over those two subsystems of their statistical precisions minus this drop of mutual information between A and C from the beginning of the process to the end of the process. So this is a way of mixing and matching thermodynamic uncertainty relations among the different components of an overall distributed subsystem, where you pick up an extra mutual information terms that's actually strengthening the entropy production bound in the TUR compared to what you would get if you ignored the underlying topology, you ignored the actual structure of the underlying multi-system basenet. Okay, so I don't know what's going on with my screen here. Okay, good. So I hope that wasn't too scattered. I'll take questions in the break, I guess, to try to clarify all of that. Some important points to note: in a multi-system basenet, we assume that the process completing the conditional distribution, the process implementing the conditional distribution at every node, that it has time to complete. So that node implements that conditional distribution in full. We assume that the sequence of which node runs when is not random. So if we go back here, for example, we're assuming that this update of that node state has to occur after this one, for example. It's got to, whatever, the precise times need not be specified, but the sequence by which the actual updates occur have to be consistent with this topology of whose update is depending on who else. So that's also being assumed in the multi-system basenet model. Go back there. And there's also in the multi-system basenet model, there's zero probability that any two subsystems change state simultaneously. As I said, this applies to many, many systems. For example, this applies to digital circuits. There's been some work on digital circuits recently. For example, a bunch of papers coming out of Massimiliano Esposito's group, David Limmer's group. I did some earlier work. There was just a couple of days ago a paper in IEEE that was related to these things. In the simplest model of such circuits, there's zero probability that any two subsystems change simultaneously. And certainly the sequence of which node runs when is not random. If it's a synchronous rather than asynchronous network, then the conditional distributions, which you hope is a delta function, deterministic process at each node, it actually completes. In the literature, what's called a multipartite process is a generalization that relaxes these first two restrictions on a multi-system basenet. You can take, just as with the multi-system basenet, we can set things up in such a way so that all the standard fluctuation theorems, TURs, et cetera, apply within any subsystem in the multi-system basenet. It's possible to do something similar with a multipartite process. What I want to show in the rest of today's talk, though, is a generalization of even a multipartite process. Crucially, a multipartite process, one way to define it a little bit more abstractly than starting from a basenet, is it's a continuous time Markov chain over a system with multiple coordinates, where crucially, under the rate matrix for the overall dynamics, there is zero probability that any two coordinates, and the coordinates can be subsystems, they can be whatever you want, there's zero probability of any two updating simultaneously. That's what it means for it to be a multipartite process. What I'm going to be showing in the rest of today's talk is that you can actually relax that condition. You can extend beyond multipartite processes. This is quite a substantial extension, actually, of the kinds of systems that can be modeled under stochastic thermodynamics. so that we can allow multiple coordinates to change state simultaneously. The TURs and so on and so forth, the fluctuation theorems, they can also be applied to individual parts of such a relaxation of a multi-part type process. In addition, you get a strengthened second law, and that's particularly what I'm going to be focusing on the rest of today. I'm going to call such things, which are generalizations of multi-part type processes, going to call it a composite process. So I just can't get, here we go. Here's an example of a composite process. This is from Freitas and Esposito, a recent very nice physical review X. This is an example of a composite process. In their particular model, it's down at the level of individual electrons jumping around stochastically between different conductors. So the conductors here, 1, 2, 3, 4. And the way that the model is set up is that when the count of that an electron goes, for example, from conductor 2 to conductor 3, that happens essentially instantaneously. When it does happen, the events in this model are that the count of electrons in conductor 3 goes up by 1 at the exact same time that the count in conductor 2 goes down by 1. So it's not a multi-partite process. These two subsystems, coordinates, as I'm referring to them, they change state simultaneously. Similarly, we could have these two change state simultaneously, or those two change state simultaneously. This is true for all of the conductors in their model. It's a composite process. Come on. Let's see. Another example of a composite process is a stochastic chemical reaction network. So for example, if we just make water out of hydrogen and oxygen, if we're doing this down at the stochastic chemical reactions, down at the level of individuals, so our variables are the counts of numbers of H2 in our system and the count of O2 and the count of H2O, then simultaneously, when this process occurs, which occurs at random times, the count of H2 will go down by 2, the count of O2 will be going down by 1, while the count of H2O will go up by 2. That happens simultaneously. So it's not a multi-partite process, but it is a composite process. And here's a last example that I'll be using to actually illustrate some of the results down below. It's a bit contrived, but it's a very, very simple example without a lot of the complexities of electronic circuits or chemical reaction networks. Consider a random walker on a two-dimensional grid, where we're going to be saying that each of these coarse-grained bins has it's L elements wide on each side. So here, L is 5. So each of these coarse-grained bins is 5 by 5. So there's a total of 25 microstates within that coarse-grained bin. And there's a total of n squared of these bins. So in this case, there's, I think it's 10 this way and 10 that way. So it's 100 coarse-grained bins and 25 microstates within each bin. And we have a random walker, just doing a two-dimensional random walk, one microstate at a time. We can have periodic boundary conditions. And here's the coordinate system I'm going to be using. X1, 1 through 5, that's where you are within a given macro bin in the X direction. X2 is where you are in the Y direction. And X3, which goes from 1 to 100, it labels the coarse-grained bin. So for example, if X3 were say 12, which is I guess this coarse-grained bin here, and X1 were 2 and X2 were 3, that would mean that you are in that particular microstate right there. Just to make life fun, let's say that in this random walk by the walker, there's a store of nutrients that extends across the space. There's nutrients along in the space, and the walker has an internal store of that nutrient. And the dynamics of its internal store of that nutrient depends only on where the walker is in X1. So that means that's actually arranged periodically, nutrient A, across this entire system. And we can also say there's a nutrient B, and walker store of nutrient B only depends upon where it is and which microstate X2 it is. So you can imagine nutrient B has some periodic distribution going up here, and which is independent of the x-axis. And as the random walker goes across the space, it picks up that nutrient in a way that depends only on where it is within that particular y-axis microstate bin within each coarse grain bin. Okay, so notice that in this particular case, to illustrate why it's a composite process, it could be that if we're going back here, for example, where x3 is 12, x1 is 2, and x2 is 3, so we're right at that state. The very next step, x1 will change. It'll only depend upon its current state. It'll be independent of the others. No other state will change simultaneously. Or x2 would change, and that would be it. x3 would not change, and we can say for simplicity, x4 and x5 would not change. Note, though, that if actually the walker is right here at the edge of a coarse-grained bin, in that particular case, it's impossible for it to go to the right, which would have x1's value drop from 5 to 1 as it goes into the next coarse-grained bin. It's impossible for that to happen unless x3 also changes simultaneously. Because of this particular coordinate system, it's impossible for x1 to change unless x3 changes simultaneously for certain values of x1. Similarly, it's impossible for x2 to change unless x3 changes simultaneously for certain values of x2. So it's not a multipartite process. It's instead a composite process where, in essence, it's a hybrid, you could say, that for some values of x1 and x2, it will you can have a change of that variable without changing this variable, but for others, that's not the case. Okay, so those are 3 examples.
And you have 4 minutes and then the question time.
4 minutes, okay. So those are 3 examples of a composite process. Here is some very, very quick definitions of a composite process. What we do, the way that we model this, is we say we have a total of n coordinates, so there are 5 coordinates in the example I just gave, and a total of r reservoirs. In contrast to multipartite processes, we're allowing these reservoirs can actually, any one of them can be coupled to a set of multiple coordinates simultaneously. So reservoir V can be coupled to a multiple set of coordinates simultaneously, and those so those can all change their state at the same time due to that coupling with reservoir V. That when they do so, when any of these states that are controlled by reservoir V change their state, they do so based upon the values in another set of coordinates, which is indicated by L sub V. P is for puppets and L is for leaders. So in reservoir V, the leaders are controlling the puppets in reservoir V. The overall rate matrix is just a normal thing. It's the sum over the reservoirs now of these expressions, which in an MPP, a multipartite process, this would be 0 if any 2 coordinates change time, but in this particular case, we don't impose that restriction. A unit is any set of coordinates such that under this rate matrix, the set of variables in that set of those coordinates evolves as a self-contained Markov process. So for example, right here, let's go back here in this particular model, because of how I was describing the dynamics of the random walker before, x1, x2, x3 is a unit. They evolve together as one overall CTMC independently of the values of the nutrients. So that's one particular unit. Another unit is given by x4 and x1. Remember, x4 is the Walker store of nutrient A. The dynamics only depends upon where it is in the microstate in the x-axis. So x4, x1 is another unit. And then x5, x2 is another unit. The end result is that there's 3 non-trivial units. So in this particular composite process, there are, in essence, one way to view it is that there's effectively 3 subsystems that each of them can be viewed as its own independent continuous time Markov chain. and it's their interactions, because, for example, notice X1 occurs in two separate self-contained CTMCs, X2 does as well. It's that overall topological structure among these units that actually gives us a whole bunch of new TURs, fluctuation theorems, and so on and so forth. But what I want to point out here, just emphasize at the end of the day, is at the end of this talk, is that due to that overlap between the units, one can also show that we have a new strengthened second law, which is determined only by that interaction networks topology and drops in the entropy. And here it is. The entropy production of any particular composite system is going to be given by the drop in the, it's a generalization of what's called total information in information theory, or multi-information, if people have come across that, total correlation or multi-information. It's the drop in the entropy of the overall system minus the change in the entropy during the process summed over each reservoir only of the units that are controlled by that reservoir, plus, and then there's going to be some overlap terms that you need to, basically it's an inclusion-exclusion principle. We need to sum back some of those drops in entropies of some of the units to make the accounting work. That's what this term gives right here. And this is in general a strengthened second law. So for example, if we apply that strengthened second law to this particular case of the active walker, remember there were three non-trivial units. And so those are, and so each one is being, so X4, so this is being controlled by its own reservoir and so on and so forth. The overall entropy production is then lower bounded based upon the overlaps between these individual coordinates. And in this particular case, for this active walker model, we can see that independent of all other details of the system, the entropy production is lower bounded by 2 times the logarithm of L. L being, if you'll recall, in this case, it's 5. It's the number of microstates along each particular axis in one of these coarse grain bins. So, boy, talk about technical difficulties. To summarize those results, in a Bayes net, the thermodynamics is in a certain sense modular. Only one coordinate, only one node together with its parents is allowed to change state at a given time. That fact, in and of itself, independent of all other details, results in unavoidable extra entropy production that is quantified by loss of mutual information, coupling the different variables as they evolve in the system. We can also use them that plug in that result into any of the standard formulas in stochastic thermodynamics that involve entropy production, the fluctuation theorems, TURs, stopping time theorems, all of them, the speed limit theorems. And here I didn't really have time to show it, but you can do that in particular in some simple examples for fluctuation theorems and for thermodynamic uncertainty relations. You generalize from Bayes nets. Relaxing some of the conditions, you will get what is called in the literature a multipartite process. In a multipartite process, it's defined as being any CTMC where no two coordinates, no two variables are allowed to change simultaneously. In many, many situations, two variables do change simultaneously. That is almost part of the definition. Chemical reaction networks, nonlinear electronic circuits, and this simple active Walker model that I showed, all of those are examples where you violate that defining feature of a multipartite process. If we want to extend all the analysis, stochastic thermodynamics of MPPs, to allow for systems that violate that condition, we get what I call composite processes, which are in essence a generalization of MPPs where you do allow simultaneous state transitions. They, just like MPPs and just like Bayes nets, have a strengthened second law, which is determined by the topology of the interactions among all the coordinates, which in the case of a composite process are determined by the overall reservoirs. So here are just 2 references. The Bayes nets work was PhysRev Letters a couple of years ago, and I highly recommend people look at that earlier one by Tsusuke and Takahiro, which was 2013, which is goes at Bayes-Nets using a different definition of energy production. They stuff about composite processes. It was published recently in Philotrans Royal Society A. There are, as is always the case with me, a bunch of typos in the published version. So I just, last night, I was madly trying to update the archive. If you look at this archive right now, which should be up, I think, by now, make sure to get V2, not V1. That is the up-to-date version of this, which has all these results for composite processes. So I think if I might be on time even, or not too badly over time. Thank you very much for bearing with me.